Suppose we have a Y-shaped tube, with fluid flowing in from the bottom of the Y, and flowing out through the two upper branches. Now let's define what a control volume is. A control volume is simply an arbitrary volume in space that encompasses a certain volume of fluid, which in this case is our fluid within the Y tube. The control volume is surrounded by a control surface, through which mass and energy can flow into or out of the control volume. Under steady-state conditions, since the mass and energy within the control volume are unchanging, we can conclude that the mass flowing into and out of the control volume is the same, and the energy flowing into and out of the control volume is also the same. Hence, for a given control volume that is at steady state, we do not need to be concerned with what is going on within the control volume. We only need to focus on the mass and energy that is crossing the control surface at the inlets and outlets of the control volume. Tanks A through H are interconnected as shown, and are all at steady state. Water is flowing into tank A from pipe 1 at a rate of 10 kg per second, while it is flowing into tank B through pipe 2 at a rate of 5 kg per second. Furthermore, tank C is being evacuated through pipe 3 at a rate of 17 kg per second. Tank H is being filled through pipe 7 at a rate of 20 kg per second. And pipe 6 is closed. What is the flow rate and direction of flow in pipes 4 and 5? This problem can be made much simpler if we choose wisely where to place our control volume. Recall that at steady state, the mass flowing into a given control volume is equal to the mass flowing out of the control volume. Hence, the summation of all the mass flow rates into and out of the control volume is equal to 0. If we simply place the control volume around the entire system, then the summation of m.1 to m.7 is equal to 0. And we get an equation that has two unknowns, m.4 and m.5, which we cannot solve. On the other hand, we can draw a control volume around tanks F, G, and H, and obtain an equation for the mass flow into and out of these tanks, which is an equation in a single unknown, m.5. We can solve this equation with the sign convention that flow into the control volume is negative, and flow out of the control volume is positive. And so we have m.5, which is the mass flow through pipe 5, is equal to minus m.6, the flow through pipe 6, which is 0, minus m.7, the flow through pipe 7, which is negative 20. Note the negative sign here because the direction of flow is into tank H. And so we obtain the mass flow through pipe 5 to be 20 kg per second. Since this is positive 20, this means that the direction of flow must be out of tank F. Similarly, we can find the mass flow rate for pipe 4. In this case, let's draw a control volume around tanks A, B, C, D, and E, and obtain an equation of mass flow into and out of these tanks, which is an equation in a single unknown, m.4. And so we have m.4, which is the mass flow through pipe 4, is equal to minus m.1, the flow through pipe 1, which is negative 10, minus m.2, the flow through pipe 2, which is negative 5, minus m.3, the flow through pipe 3, which is positive 17. And so we obtain the mass flow through pipe 4 as negative 2 kg per second. Since this number is negative, this means that the direction of flow must be into tank D. In its most basic form, the principle of conservation of mass means that mass can neither be created nor destroyed. Hence, as we have seen before in our explanation of the control volume approach, for a control volume that is at steady state, the mass flowing into the control volume must be equal to the mass flowing out of the control volume, in order to satisfy the conservation of mass principle. In equation form, for a control volume that is at steady state, the conservation of mass principle can be expressed as the summation of all mass flow rates that are going into the control volume is equal to the summation of all mass flow rates that are going out of the control volume. Assuming that the velocities at all inlets and outlets of the control volume are uniform and parallel to the control volume's area vectors at these inlets and outlets, as we did in our discussion of the mass flow rate, we get that the summation of the density times the total area times the velocity at all inlets is equal to the summation of the density times the total area times the velocity at all outlets of the control volume. If we assume a single inlet and a single outlet for the control volume, we can drop the summation operator, and we now have the shown equation. Finally, for an incompressible fluid that has a constant density, we can cancel out the density from both sides of the equation, and we end up with the relation that the surface area of the inlet times the velocity at the inlet is equal to the surface area of the outlet times the velocity at the outlet. Water is flowing through a circular pipe section that has a diameter of 10 centimeters in location 1 and a diameter of 20 centimeters in location 2. The velocity at location 1 is measured as 10 meters per second. Assuming the velocity in the pipe is uniform and parallel to the pipe's walls, what is the velocity at location 2? And what is the mass flow rate through this pipe? We start by applying the continuity equation between points 1 and 2, where the cross-sectional area of the pipe at point 1 times the velocity at point 1 is equal to the area of the pipe at point 2 times the velocity at point 2. This equation can be rewritten as V2 is equal to A1 over A2 times V1. We can then calculate the areas at 1 and 2, using the pipe diameters at these locations. So we substitute 0.1 meters for D1, and we find that A1 is 0.00785. And we substitute 0.2 meters for D2, and we find that A2 is 0.0314. And so we have V2 is equal to A1 over A2 times V1, and get a velocity of 2.5 meters per second at point 2. Next we need to find the mass flow rate through the pipe. The mass flow rate, m dot, is equal to the water density times the cross-sectional area of a location along the pipe times the uniform velocity at that location. We can choose either location 1 or location 2 to calculate the mass flow rate. Shown here is the calculation based on location 1. So we have ρ water times A1 times V1, which gives a mass flow rate of 78.5 kilograms per second. In its most basic form, the principle of conservation of energy means that similar to mass, energy can neither be created nor destroyed. Hence, as we have seen before in our explanation of the control volume approach, for a control volume that is at steady state, the energy flowing into the control volume must be equal to the energy flowing out of the control volume, in order to satisfy the conservation of energy principle. There is, however, a major difference between mass and energy conservation. Mass can only flow into or out of the control volume when carried by the flow through a part of the control surface that is an inlet or an outlet. In other words, mass cannot pass through a solid wall. On the other hand, energy can pass through a solid wall, and hence can flow into or out of the control volume, through any part of the control surface. Whether it is an inlet or an outlet, or a solid wall. Consider the shown control volume that has an arbitrary shape. There are three types of energy that can flow through the control volume. The first is flow energy. This is energy that is carried into the control volume by the incoming flow through the control volume's inlets, and out of the control volume by the outgoing flow through the control volume's outlets. It is expressed by the variable capital E dot. Flow energy cannot penetrate through a solid wall, and it can only enter or exit the control volume through an inlet or outlet when it is being carried by the flow. The next two energy types can flow into or out of the control volume, through any part of the control volume's surface, even if it's not an inlet or outlet. Work energy can be work done by, or on, the control volume, using a mechanical device, such as a shaft that is connected to a propeller, or by a piston. It is expressed by the variable capital W dot. The third type of energy is heat energy, which can flow into or out of the control volume, due to a temperature difference between the control volume and its surroundings. It is expressed by the variable capital Q dot. In our current study of the conservation of energy, we will only consider energy flowing into or out of the control volume, while carried by the flow through an inlet or an outlet. We will not consider work or heat energy. Consider a certain mass m, of a fluid that is contained in the shown cylinder. We wish to quantify how much energy is contained in that fluid mass. We express the total energy content of the mass m, of the fluid, by the variable capital E, which has units of joules. The total energy contained in the mass m is equal to the mass m, in kilograms, times the energy per unit mass contained within that particular fluid mass, which is written as small e. The energy per unit mass, or small e, has units of joules per kilogram. If we now imagine that the shown cylinder is actually a pipe, through which a fluid is passing, then we can determine the rate at which energy is being carried by that fluid through a given pipe cross-section. The rate at which energy, being carried by the flow, is passing through the pipe, is expressed by the variable capital E dot, which has units of joules per second, or in other words, watts. E dot is equal to the mass flow rate, m dot, which has units of kilograms per second, times the energy per unit mass of the fluid, or small e. In terms of the energy per unit mass content of a certain amount of matter, we can consider 6 types of energy: nuclear energy, molecular bond energy, internal energy, pressure energy, kinetic energy, and potential energy. Potential energy can further be divided into potential energy due to a gravitational field, an electrical field, and a magnetic field. Hence the total energy content per unit mass of a given amount of matter is the sum of all the aforementioned energy per unit mass forms, for that particular amount of matter. In our current consideration of this subject, we will neglect any energy type that does not change. Hence, assuming no nuclear or chemical reactions take place, we can neglect nuclear and molecular bond energy. Furthermore, assuming the temperature of the fluid remains constant, we can neglect internal energy. Finally, assuming the fluid is not electrically charged or magnetized, or is not moving within an electric or magnetic field, we can neglect potential energy due to electric and magnetic fields. We are thus left with pressure energy, kinetic energy, and potential energy due to a gravitational field. As we have seen in the previous section, the energy per unit mass equation for a given mass of fluid can be simplified to include only the pressure energy, the kinetic energy, and the potential energy due to gravity. The pressure energy per unit mass contained in a given mass of matter is the energy content in that mass due to it having an internal pressure that is more than that of absolute vacuum. For a fluid at high pressure, one way of converting this energy to potential energy, for example, is by allowing the fluid to expand, while lifting a weight up against gravity. In this case we relax our usual assumption of the fluid being incompressible, to it being nearly incompressible, in order to allow for the fluid to store pressure energy by slightly contracting under the effect of outside pressure. The pressure energy per unit mass is equal to the fluid's internal pressure, divided by the density of the fluid. The kinetic energy per unit mass contained in a given mass of matter is the energy content in that mass, due to it having a velocity relative to a stationary frame of reference. The kinetic energy per unit mass is equal to half the fluid velocity squared. The potential energy due to gravity per unit mass relative to a reference location is equal to the gravitational acceleration times the height h above that reference location. By substituting the expressions for pressure, kinetic, and potential energies per unit mass, we obtain the shown equation for the total energy per unit mass of a fluid. For all three energy forms, after substituting for the units of the variables, and simplifying, we see that we get the usual energy per unit mass units, of joules per kilogram.